Today we're taking a look at the absolute value function. Now the absolute value function looks like this: f of x equals the absolute value of x. And if we take a look at the graph of that, it looks like this V-shaped graph here with its vertex here at the origin, its reflection symmetric over the y-axis. Its domain is going to be the set of all real numbers, and its range is going to be the set of all real numbers greater than or equal to 0, which should make sense because the absolute value really just measures the distance a number is away from 0 on the number line. And distance can never be negative. It's always positive. All right, let's talk about square roots now. Square roots and absolute value functions are somewhat closely related. For all real numbers x, the square root of x squared is equal to the absolute value of x. That is, when x squared is positive, the square root of x squared has to be equal to both the positive and negative values of x. We'll show you what we mean here with an example. If I take the square root of 64, you'd say that's easy, that's 8, because 8 squared returns 64. However, if I take negative 8 and square that, I'm also going to get 64. So you see the square root of 64 is not just 8, but it's both the positive and negative values of 8. All right, let's take a look at example 1. We simply want to evaluate the absolute value of negative 9, and you know that's just positive 9. But on a number line, if we take and plot negative 9 here and measure that distance between that point and 0, we know that that distance, even though it falls to the left of 0, that distance is still positive. So that's just your visualization of what the absolute value really means. All right, in example 2, we see that we want to solve 3x squared is equal to 18. Check your work by substituting your solutions back in. So we're going to start by trying to get x by itself. I'm going to divide both sides by 3 first, and that gives me x squared is equal to 6. Now to undo a squaring, I would take the square root of both sides. And when I take the square root of both sides, I have x equals, and again, here I'm taking the square root of a positive number. So I have to allow for both the positive and negative values of the square root of 6 to be solutions here. So I say x has 2 solutions. It's the positive and negative value of the square root of 6. Now, substituting that number back in, I would say 3 times the square root of 6 squared should be equal to 18. When I square the square root of 6, I get 6. So 3 times 6 is 18. Check. Now, if I put the negative value of the square root of 6 in there, if I take negative square root of 6 times the negative square root of 6, again, I get 6 back, and 3 times 6 is 18. So both of my solutions work. Okay, now you should start to see a little bit of a resemblance here when we start solving absolute value functions. Remember, absolute value measures the distance a number is away from 0. So really what this expression says is that there is some number x such that the distance that number is away from 0 is 15. Well, on a number line, if we were to go 15 away from 0, I would actually end up at two different points. I would end up at positive 15, and I would end up over here at negative 15. So I actually have 2 solutions for this equation as well. Now here's how we go about solving this. We say that when you drop the absolute value bars, you have to write 2 equations. One equation is set equal to the positive value of the other side, and the other equation is set equal to the negative value of the other side of the equation. So that's where we get x equals both positive and negative 15. Okay, let's apply that same thing now to this next problem here. It says to solve this for x, we have the absolute value of 34 minus 2y equals 12. So right away, we've isolated our absolute value signs. We're going to drop those bars. And when we drop the bars, we have to set it equal to both the positive value of 12, and we have to set it equal to the negative value of 12. So we actually end up with 2 equations, and now we need to solve both of them. Subtract 34. We have negative 2y is equal to negative 22. Divide both sides by negative 2. and we have y is equal to 11. So there's one possible solution. And the other possible solution, again, we're going to solve for y, subtract 34. And we get negative 2y is equal to, that's negative 46. Divide both sides by negative 2. And we get a y value that's equal to positive 23. So we say that we have two solutions here, both y equals 11 and y equals 23. All right, in example 5, here we see that we have a square and a triangle that have the same area. The triangle has a base of 7 and an altitude of 6. So let's start off by drawing ourselves a square. Here's a square. Its area is known as side squared, or base times height, but base and height are the same for a square, so it's just side squared. A triangle is base times height divided by 2. So we see that a triangle has a base of 7 and its height or its altitude of 6, and we're going to divide that by 2. So that 7 times 6 is 42, divided by 2 is 21. So the area of my triangle here is 21, and we see that the triangle and the square have the same area. So I know that s squared must be equal to 21. So to find the length of that side of that square, I'm going to take the square root of both sides. And I'm actually going to leave it as a square root of 21 because that's approximately like 4.5-ish, somewhere in there. Now, the reason why I don't give the negative value of the square root of 21 is because we're talking about the length of a side of a square. And length, like distance, cannot be negative. All right, a few last examples here. We're going to look at Desmos here and do a few graphing. So let's start off in example 7 by graphing the equation y equals 4 and graphing the equation y equals the absolute value of x minus 2. I've actually done that over here on this Desmos sketch. So you can see here's my horizontal line of y equals 4. And y equals the absolute value of x minus 2. It looks like it gets shifted 2 units to the right, and I can see their intersection points here are negative 2, 4, and 6, 4. All right, we'll take a second now to graph those equations. Here's 1, 2, 3, 4. Here's my horizontal line, and here is my absolute value function. Whoops, I missed that a little bit. And I missed that one a little bit. That's supposed to go through that point there and that point there. So I see that I have two solutions. Now those two solutions are at these intersection points, and that's the coordinate 6 over and 4 up and the coordinate negative 2 over and 4 up. And if we solve this absolute value equation here by hand, I am going to drop the absolute value bars by writing two equations, setting one equal to the positive and one equal to the negative, and solve. I'm going to add 2 to both sides here, so this gives me x equals 6, and if I add 2 to this side here, I'll get x equals negative 2. So again, these are directly related to your intersection points that you see between the line of y equals 4 and y equals the absolute value of x minus 2. All right, I want you to go to Desmos now, and I want you to graph the two equations, y equals negative 3, this should be a horizontal line passing through negative 3, and y equals the absolute value of 2x plus 1. Tell me if there's any solutions there, and if not, tell me why there aren't.